Hello guys, welcome to Deep Codes, and in today's video we will discuss LeetCode question 2646 that says minimize the total price of the trips. So guys, you are given a tree with n nodes numbering from 0 to n minus 1, and along with that you are given this edges array that denotes the edge between two nodes A and B. Further, each node of a tree has some price associated with it. So let me close this dark mode. So yes, you can see that there is some price associated with each node, and further you are given one trips 2D array. So this trips 2D array contains start and end, start node and the end node, and what you need to return is you need to return the minimum total price sum to perform all the given trips. So see, firstly you are given how many total nodes are there, then second you are given edges between those nodes, third you are given prices of each node, fourth input is trips that contains multiple trip with a starting and the ending node. Okay, clear till here? And we need to return minimum total price sum to perform all given trips. So what I think here is, see, we can halve the price, we can reduce the price of a node to its half. Okay, so before performing your first trip, what you can do is we can choose some of the non-adjacent nodes and halve the prices. See, non-adjacent nodes. So let's say one node is node 2 and node 1. See, they both are adjacent. So you cannot halve the prices of both the nodes. Either you can halve the prices of node 2 or node 1, but not both. Correct? So you can halve the prices of the sum of the nodes, and that nodes must not be adjacent to each other. Okay, clear till here? So by performing this step, we need to find the minimum total price sum to perform all the given trips. Now guys, if you take a look at the first example, here, let me again change to dark mode. Okay, so these are the prices of the nodes, and yeah, this is the edge between the nodes. Now here guys, what are the trips given? So one trip is from node 0 to node 3. So this is 0 to 1, 1 to 3. Another trip is from 2 to 1. This is 2 to 1 trip, and another trip is from 2 to 3. That is 2 to 1 and 1 to 3. So these are this way you are given 3 different trips. Now you need to select such node that the minimum sum of all doing all the trips is as minimum as possible. Okay, the total sum is as minimum as possible. So you need to select the nodes in such a way to reduce the overall sum. So here what we did is we selected this node, and this node. So these 3 nodes that we selected here to perform our trips, and see, these are not adjacent. So we selected these nodes. Selected, that means we reduce the price to half of these nodes. Okay, got this? So we reduce from these to these. So these nodes prices are reduced now. So by after doing this, if you calculate the cost of the trips, see, cost of trip 0 to 3 is what? Node 0 to node 3 is 1 plus 2 plus 3, 6. This is what? 6. From 2 to 1, 2, node 2 to node 1 is 7, and 2 to 3, 2 to 3, that is 5 plus 2 plus 3, that is 10. So 10 plus 7 plus 6, it is 23. So as you guys can see, 23 is as our answer. So thus by reducing the price of some of the nodes that are not adjacent, we can get the minimum sum. Okay, now here you are given this 0, 1 tree, and both with a value 2. So you can select either of these nodes and convert one of the nodes to half of the prices, because there are only 2 nodes and they are adjacent. So this 2 we reduce to 1, and now if you do the trips, then we can get the minimum output. See, here the trips are only 0 to 0, means there's only one node that we are traveling in the trips. So it is better that we reduce this cost of this node instead of this. Okay, so guys, the only complexity here in this question is to choose the nodes whose prices has to be minimized or halved, right? We have to efficiently or optimally choose some of the nodes that are not adjacent, as well as by reducing their prices to half will give us the minimum possible answer. Okay, now after listening to this word non-adjacent nodes, so non-adjacent nodes, so you might be getting one point in your mind that how you can get non-adjacent node. So this is something similar to bipartite graph. So bipartite graph is nothing but we are simply coloring the graph such that adjacent nodes are not same. this is nothing but coloring graph such that adjacent nodes are not same color. So here also we are doing something similar like this, that if the one of the node is price is reduced to half, then adjacent won't be reduced. So something like this we are doing. So let's say here you are given this type of tree. Node 0 with a value price 10, then node 1 with a price 6, node 3 with a price 8, node 4 with a price 14, and node 2 with a price 12. And if you are given some trips like this, only one trips, let's assume only one trip from 0 to 4. Okay. So now if you apply this logic of bipartite graph, that means either you reduce the price of this, let me take this, either you reduce the price of this node, node 0 and node 3, or you choose these nodes, node 1 and node 4. So they are not adjacent. So this is what bipartite graph does. It colorizes the adjacent node with a different color. Okay. So let's say if you choose these nodes, so then they both are non-adjacent. So we can reduce the prices to half. So let's say half node 0 and node 3 prices are half. Prices half. So after that, what would be the overall or total sum? It would be 5 plus 6 plus 4 plus 14. See, 10 is reduced to 5 and this 8 is reduced to 4. This is the total sum, and let us sum it. So this is 14 plus 6, 20, 24 plus 5, 29. Now if you choose this node 1 and 4 to be reduced to half, so node 1 comma 4 prices half. So then after that, what would be the sum? 10 plus 3 plus 8 plus 7. See, these 3 and 7 are the half prices, and after, what is the sum of this? It is 10 plus 8, 18, plus 3, 21, plus 7, 28. Okay. Now if you use, so guys, if you use the bipartite logic, that not choosing the adjacent node, and taking this the node at so taking here, what we are doing, see, let me also explain you like this. This is level 1, level 2, level 3, level 4. So in a bipartite, what we are doing, if you are choosing level 1, then you will choose level 3, right? If you are choosing level 1 node of nodes to be half, then you will choose level 3. That is nothing but, if you are choosing level x, then you will choose level x plus 2. Okay. Similarly, if you are choosing level 2, then you will choose level 4 nodes. Okay. This is what we do in the bipartite. But do you think, is this a best possible answer, or can you get better answer than this? What if I say, if you reduce the price of a node 0 and node 4, if you reduce the price of node 0 and 4 price half, then what is your answer? So it would be 5 plus 6 plus 8 plus 7. 5 plus 6 plus 8 plus 7. What is the sum? See, 6 plus 5, 11. 11 plus 8, 19 plus 7, 26. See, didn't you get very much the best possible answer, or the most optimal answer? Yeah, got it. So and also, if you notice, this 0 and 4, node 0 and node 4, they are not adjacent. But if you take bipartite graph logic, then some of the test cases won't pass here. See, ultimately we need to choose some of the nodes that are not adjacent. But if you take this level by level using bipartite, then some of the cases might fail. So cases like this, okay, understood, where the bipartite logic didn't work. So yeah, that's why what we have to focus on, only one thing, that each node has two choices to take. So here take means half its price or not take. Okay, right? Each node has two choices. Okay, and whenever, guys, you have something like choices, then at that point what we can do is, we can write a recursive solution and memorize it. See, whenever you have choices like this, take and not take, what we can do, we can write recursive solution and memorize it. Okay, so the same thing we will do here today, that we will write a recursive solution and then we will memorize it recursive solution. Now, what another thing we can do here is, see, we are given this strips array. This strips array contains nothing but a start and end, different start and ending of our trips. So what we can do is, we can pre-calculate the frequency of node using all the trips. Okay, we can calculate the count or frequency of node used in trips. Okay, let's say let's say for this only example, let me take the example again. Let me copy this. So guys, for this only example, if you are given trips like this, 0 3 2 4 1 4, then what we will do is for each node 0 1 2 3 we will get the count. Okay, I will explain you why we need this to do. So here in this first trip 0 2 3, how many nodes are there? 0 1 3. So increment the count. This is the count or frequency, you can say count, and these are the nodes. So increment the count by 1. In the second trip 2 to 4 we have 2 0 1 3 4 all plus 1 plus 1 plus 1 plus 1. Here 4 is also there, plus 1. And in the last trip 1 to 4 we have count like plus 1 and plus 1. So if here we will take this count or frequency and we will form matrix like this, sorry, matrix not, we will form an array or a vector like this. The count 2 4 1, no 2 3 2 3, here frequency is 3, here 1, here again 3 and 2. So we will form this. Now why we require this? Because this will help us to calculate the total so this will help us to calculate the total price of all the trips. This will help us to calculate total price of all trips in big O of 1. In a constant time complexity, you can calculate the total cost of all the trips, correct? Right? If you have count of all the nodes, then you can directly calculate the price of all the trips. Okay, so now we will combine this logic plus recursive logic and build our solution. So guys, now to solve this question, we will take the same example. These are the trips and this is the count that we have already seen in a dry run. So let me show you the same in the coding part here. So initially we initialize this count vector to the 1D vector count, and then here we created one adjacency matrix and we push all the nodes that are there based on the edges. So based on the edges we created the graph like structure with the help of adjacency matrix. This is just to resize our count vector, and then here we are counting all the nodes that are there in all the trips. So we are traversing each trip from the starting point until the destination. So each trip has some start and the end point, and yeah, we are calculating and processing the count. So for that, what we are doing, we are simply making a DFS call until the current node is a destination node. So this is nothing but a simple DFS for loop where we check if the node is not equal to parent, then only we call this function again integrate count, and then we also increment the count of this ith node and we return true. Okay, else we return false, means this is just to start and end the function call. Okay, now after we get the count, then here I am calling this function dfs solve. So inside this dfs solve I have taken a few parameters that you have to keep in mind. So first is node, parent, bool parent taken, vector int price, and this is adjacency matrix. Now see, let me show you one simple thing. Here we have node 0, then below it is node 1, and after this is node 3. See, this is the parent, this is assumed parent, this is current node, and this is its child. Okay, keep an eye on this. See, for each node has one parent, right? Each node can have one parent and n number of child. Okay, clear till here? Each node has one parent and n number of child. Here here one can have multiple, like n childs, right? It's n childs, but only one parent. Okay, so now so this is the DP. We will talk about this in a later. First, understand the recursive part. So first thing, here what we are doing is we are simply calculating the number of childs. Okay, how many child are present at the current node? See guys, this is the current node. Now we first calculate how many childs are there, and in the end increment this variable childs. Now if number of childs is 0, so if there are no child, then what we can do is we will stop if the number of childs are 0. if the number of children are, if there are no children only, then there is no meaning to make a recursive solution, right? Then at that point, this is how we will terminate our recursion. Okay, clear till here? So if a child is 0, if the number of childs are not there, there are no child from the current node, then what we will do, we will check for this condition if the parent is taken. Parent taken means nothing. If the parent price is halved or not, that we will maintain. So if the parent price is halved, then we cannot reduce the price of the current node. We cannot reduce the price of the current node. But if this condition is failed, then what we can do, we can reduce the price of the current node, right? So that same thing we will do. We will reduce the price of the current node if the parent price is not taken. That means if the parent price is not halved. Okay, now this was the scenario if the child is if the number of childs is 0. This is the terminating condition where we have reached a point where there are no child is there. Now further, if the number of childs are more than 0, then this condition we will come across this condition and this condition. So if so here this condition will be failed because this current node 1 has one child, right? So this condition will fail. Now if the parent would be taken, if the parent was taken, right, if the parent was taken, then the current node can't be taken. That means the current node value cannot be reduced to half. So that only same thing we are doing. If the parent node is taken, then we won't reduce the price of the current node, but for the child node we have choices, right? For the child we have choices, either to reduce the price or not. So that's why for this child a parent would be the current node. So here we pass the false. See, if you look here, node, parent taken. Now what we are doing here, we are iterating all the child node of the current node. Now it is sure, then since the parent, since the parent is taken, the current node we won't take, this price cannot be reduced, so all its children price can be reduced, right? So so we are making here a recursive call and passing parent taken to false, because for all the child node I of the whose parent is node, now since the parent node cannot be taken because node's parent is already taken. See, current node parent is this, 1 is the current node, its parent is 0, 0 is taken, you cannot take node 1, so we will pass false here. Okay guys, clear till here? Since the current node is not taken, we will pass false, and at the end we will simply update, since we are storing our answer here, and here we are then we are adding the current node price also to our answer, and we will return that. This is one condition. Now another condition is, let's say if the parent is not taken. Now if a parent is not taken, then we, for the current node we have two choices, either to take and not to take. So yeah, that's why I initialize two answer variable, answer 1 and answer 2, and I run this for all the adjacent node or all the child of the current node, for all the child of the current node. And if I not take a current node, so if I not take the current node, so I am passing it as false. So I is child, current node is node, but the node is a what? This node is a parent of I. Now since I am not taking this current node, so I pass as false, and if I take the current node, I pass as true, because I have, for the current node I have two choices, not to take and take. And if I am not taking in the answer 1, I am not taking, so that's why I haven't reduced the price in answer 1, but in answer 2 I am taking, so yeah, I reduce the price. See, dividing by 2 I am doing here. So that's why I pass true here, the parent taken is true. In the answer 2 I am storing for that scenario. So guys, clear till here? So this DP, so this was the recursive solution, and to memorize it we simply use DP. Now what are the changing variables here? Only changing variable is the node and the parent taken. These are the only two changing variable. Okay, the node, so there are 51 number of nodes are present, and parent value can have two values, true or false. So we can store, so I took this DP of size 51 and 2. There are 15 nodes and 2 possibilities, so I took this DP and I first check this, if a DP of node and parent, this combination is already calculated, then return its answer. Else every time store it in the DP, right? Every time before a return statement, store it in the DP. So guys, clear till here? Let me brief this out so that you have better understanding. See, for each let me take it here. So for each node, a node can have one parent and children. Now first thing what we check here is that if number of children, if the number of children is equals to 0, then stop. If there are no children, then stop. If this is not if this is greater than 0, then recurs. Okay, then make a recursive call. Now how you will make the recursive call? Then here second step. Now if a parent is taken, so current node can't be taken, right? Okay, so current node can't be taken, so children of current node can have choices, right? So if for this we will pass false for the parent taken. For while by making a recursive call for the children, we will pass false. And now the third possibility, parent not taken. Then we have two choices. Then when we store in answer 1 and answer 2. Here in answer 1, what we do, we take let's say we not take current node and pass false, right? And pass false. Take as we have current node, this is another possibility, and pass true in recursion call. So this same thing we are doing in answer 1. We are not taking the current node, so we pass false, that is for the children of the current node we pass false, that is parent taken is false, else we pass true. And then in the end we took the minimum of both the answer, so that we can get the minimum overall. So guys, I hope you have now somewhat understanding of how to solve this question. The first thing we looked at by bipartite solution won't work. The second thing we look at what are the choices that are given in each node. The third step we look at how to get frequency of all the nodes and why it will help us to get the answer. Then we move on to the coding part and learn what are the different possibilities, and we maintain all those possibilities in our code. So guys, now talking about the time and space complexity. The time complexity for this solution is big O of n into t, that is the number of nodes into trips, and the space complexity is big O of n. So now explaining this, then see this will take what n into t, that is number of nodes into how many trips are there. This get count function will call t number of times how many trips are there, and each time for n nodes. So this is the time complexity for this. Now here, since this dp is a constant space, 51 into 2, so this is a constant space, so the time taken by this DFS solve will also be constant. So that's why we are not adding here in for this recursion function call here in the time complexity, because we are simply filling this dp and it is of a constant space, right? And talking about the space complexity is big O of n, because here we are using this count variable for n nodes. So yeah guys, that's all for this video. If you guys have still any doubts, then do let me know in the comment section. Make sure you like this video and subscribe to our channel. Thank you.